It's my pleasure to introduce Vandana Singh, who's a professor of physics at Framingham State University. She's a former particle physicist, currently engaged in transdisciplinarity. Oh, that's much better. See, now I can see that I said that it should have been transdisciplinary. I made up a new word. Scholarship of climate change with emphasis on new conceptualizations in climate pedagogy. She conceptualized and ran the first interdisciplinary workshop in Massachusetts on teaching climate change for high school science teachers in the summer of 2017, and was an invited speaker at the National Academy's Workshop for Interdisciplinarity in STEM in 2016. 2014, she was granted a program award by the American Association of Colleges and Universities to develop a case study for undergraduate education, for which she traveled to Alaska to study climate change at the intersection of science, policy, indigenous culture, and justice. Professor Singh has been learning about climate science and teaching it in general physics college courses for over a decade. So we are very thrilled to have her here, and please help me welcome to the stage Professor Singh.
Hi everyone, can you all hear me fine? All right, it's such an honor to be here. Thank you for inviting me, and it's always such a pleasure to be in the company of fellow educators. So I'm looking forward to sharing my ideas and also hopefully hearing yours and having a discussion. So, well, first I have to figure out how this works, so let me just make sure I do that first. Yeah, okay. All right, so I'm going to try to answer one of the questions that one of you posed, Rajeshri posed that, I believe, that if you're not teaching an earth science course, how do you put climate science into it, or climate change into it in general? And this is something that I hope my talk will help people understand, at least one way of doing it. So this warning from world scientists came out only 3 days ago in the Journal of Bioscience, and essentially saying, this is one of many warnings that have come out over the years, that we have a climate emergency. We have a global emergency, and that planet Earth is facing a climate crisis that is going to cause untold misery to the millions and millions of its inhabitants, its human and other inhabitants. So when I first started on this journey of where my background is in particle physics, I used to study quarks a long time ago. And I love quarks, don't get me wrong. But when I started on this journey, there were fewer, the warnings weren't as loud at that time. It was about 2007, not that long ago. But I started hearing about the climate crisis, and I started wondering if it was really something to be concerned about. A physicist is generally innocent of earth science. So I woke up. And so this was my journey from someone who pondered the inner mysteries of subatomic particles to someone who was trying to learn about the planet on which we stand. And as a result, I have developed total geologist envy. But anyway, so this is what I thought about then, and I still think now, that if anthropogenic climate change is real and serious, we are ethically obliged to teach it and communicate it, because we are in a very, very important position as people with a large ripple effect, as people who can influence the future. And that this should be true no matter what the subject is, whether you're teaching literature or political science or chemistry or physics or biology or whatever. So this was the position that I took and I told myself. And I'll tell you how I started and some of the mistakes I made. Hopefully, it'll be illuminating. So this is how I started. I said to myself, well, it can't be that difficult. After all, the greenhouse effect is like one hop, skip, and jump away from where I teach electromagnetic spectrum in my general physics course. And carbon dioxide, why it's a warming gas? Well, you learned the dance of CO2 from Dr. Archer. I teach that to my students. And that connects with oscillations. So this is a no-brainer. I just have to do that. And the only thing I really have to throw in is the evidence that climate change is real and human-caused, and the impacts. And what I thought I was doing back then in 2007, 2008, and so on, is that I thought I was giving students who would not otherwise have a chance to learn the basics of climate science, the tools, the equipment, the knowledge, so that they could be forewarned and forearmed, all right? Until I started collecting, or I started getting feedback from students, which was something like this. So there were a variety of responses I've collected over the years, and many of them are in the territory of, well, we're screwed, or this is the most depressing thing ever, or like, Professor, what can we do? Can we stop talking about it and do something? Or, hey, I'm just one person. There's nothing I can do about it. Or, it's not bothering me. It's not changing my life, so why should I care? Or, well, well, I'm sort of concerned about it, but no, I don't ever bring it up with anyone. Or someone's going to invent something and fix this for us. And then questions like, doesn't it have to do something with the hole in the ozone layer? And then, if carbon dioxide is so bad, does that mean that we shouldn't be breathing out? and then, well, maybe, and you can tell that this second to last comment was probably in the spring semester in February in Boston. Why can't we wait until Boston is like North Carolina before we fix it? And then, of course, I've also heard, although this was only from one student very recently, that, well, scientists have to do what the funders say, don't they? So how can we trust what they're saying? They're doing it for the money. So when I started collecting these misconceptions, it led me to this conclusion that simply teaching A, just the bare bones of the science, and B, just the science alone was insufficient. So I started looking into interdisciplinarity, and partly that's natural for me because I love all the realms of learning, like throughout the spectrum. And you know, when I was forced to choose one thing over the other, then it was tough because in India, in 10th grade, they make you choose between science, the arts and humanities, and commerce. So I had a tough time doing that. But anyway, so to interdisciplinarity, when you have two or more disciplines that are combined in an integrative way. Transdisciplinarity, when you don't assume disciplinary walls in the first place, and you transcend those walls to create a new model. So what I learned over the years is that climate change by its very nature is transdisciplinary, and that justice issues are inextricably entangled with it. And that's partly because I'm privileged to work at an institution which serves a lot of working class Americans, and where my students work really, really, really hard to pay for college. I know that some of you probably teach at similar institutions. And they are amazing people. They're amazing human beings, and they are more intelligent than they know, you know, and and I was really kind of almost heartbroken at some of their responses because their lives are so heavy with so many responsibilities, many times for family, for parents, and so on and so forth, that I was kind of depressing them out of their minds with this stuff. So, but also it was brought home to me how inextricable justice issues are from the climate issue when I took a trip to Alaska. But just to get a sense of where you all are coming from, let me just ask you, if you don't mind, how many people here are from STEM backgrounds, if you'd raise your hands? And therefore, how many are from non-STEM backgrounds? Okay, so we have a really good mix. So I'm hoping that I'm able to speak to both sides. So here is a picture of me on the beach. That's the picture on the left. This is the beach in a town called Utqiagvik, formerly known as Barrow. It's the northernmost point in the United States on the north shore of Alaska. And I was there to actually come up with a real-world case study-based education tool for the AAC&U. And I chose Arctic climate change as my topic because, as many of us know, the Arctic is ground zero, or one of the ground zeros for climate change. So there I am on the beach with the frozen Arctic Ocean behind me. And then the other picture I'm going to explain in a moment. So when I was there, I realized a number of things. I talked to Inupiaq natives. I talked to scientists. And in fact, much of the population of Barrow consists of Inupiaq natives and scientists. What I learned was that the rapid vanishing of sea ice and the thinning of sea ice year after year after year was actually becoming a threat to the cultural identity, but also to the survival of the native peoples who had been there for 4,000 or more years. And that the ancestral memory that was carried by the elders of the tribal peoples actually did not have anything like what was happening today. And many of their traditional occupations, for instance, in winter, they rely on subsistence hunting to survive, were being threatened by climate change. At the same time, they depended on the oil industry for the conveniences of modernity, for living a settled life without the difficulties of their prior existence. So to me, that illustrated two things. One is that the Inupiaq natives had not caused climate change, and yet they were having to deal with the worst impacts. The other thing was that they had insights about how to deal with this, even as they were struggling through those things. And that part of their dilemma was actually our dilemma too. Do you go with short-term convenience and comfort and sacrifice your future, or do you find some other path? Except that we are insulated from it by the layers that modern industrial culture offers us. So the justice issue became apparent to me then. And then more recently, and if I have time, I'll talk more about this, but I just want to mention that I've started to work with marginalized communities in India, where the communities are being threatened by, not just by climatic changes, but by severe inequality and by so-called development projects. And the picture over there shows some women, some village women who have not had a day of formal education, who are protecting their local forest. And if I have time, I'll talk more about that. But all of this brought home to me that I needed to think about justice and how that entangled with the whole thing about climate. So I started thinking about what is an effective pedagogy of climate change. And my definition, over the years, this is where I am right now, it's always a work in progress, but this is my definition, that an effective pedagogy of climate change, firstly, must equip the student with a fundamental understanding of basic science impacts and evidence. And one essential aspect of it is the complex, nonlinear nature of the climatic system, and also a way to look at proposed solutions and future predictions and understand different scenarios. So in other words, a scientific technological dimension. But I also consider an effective pedagogy to be one where the student can understand societal and ethical implications of climate change, in other words, climate justice, but also the intersections with economic, cultural, human rights, sociological issues, and to critically examine proposed climate solutions from a climate justice perspective. And this is the transdisciplinary dimension. This would also be a pedagogy that enables the student to see the climate crisis as a symptom of a social scientific framework or paradigm, a framework, a mental model, a way of thinking about the world, and therefore to understand and articulate the need for new social scientific frameworks. So this is the epistemological dimension. And ultimately, the bottom line, which was the original motivation with which I started introducing the topic of climate change in physics courses, was the psychosocial dimension, that I wanted my students to go out in the world and say, we are going to make change, and we are going to make change the right way. And so these are, for me, the keystones of an effective pedagogy. So what are the challenges? Well, there's so many of them, and this is only one way of slicing the challenges, but I'm just going to mention a few things. The things that my approach tries to embrace, a lot of it has to do with the fact that students don't come in with open blank slate minds. They come in with stuff they've heard. They've come in with what's in the cultural atmosphere. And there are a lot of misconceptions out there, even among those who accept the reliability of climate change, the evidence, there are a lot of misconceptions out there, as this is something that I myself had to learn, sometimes the hard way. So the things that I want to talk about today particularly have to do with transdisciplinarity, really interdisciplinarity at this stage, but if we have time, I want to talk about how to transcend the disciplinary barriers. But also, as you can tell from the student responses that I showed you earlier, there's psychological barriers. Students sometimes react with apathy or denial, although I have rarely over the last few years had anyone outright deny the validity of the evidence on climate change. So we have to deal with that, and especially those of you who have to work with much younger students than an undergraduate really have to think about the psychological impact of what they're learning. So I'm going to be talking a little bit about that and some ways I've found to get through that. And then, as I said, I'm going to mention a few other things about the epistemology and so on. And I think that many of you may have come across this result that from a paper in Science a few years ago, that 75% of science teachers in the US teach at least an hour about global warming, but that we're asking teachers we're actually being really unfair to teachers in one sense, asking them to teach something as complex and challenging as climate change without giving them the adequate preparation. And that's partly because nobody actually knows how to do this stuff. Climate pedagogy is a really new field. So when I come to you on this podium, I'm doing so with the utmost humility because I'm trying to find a way, as many of us are trying to find ways. And I hope that we're all going to share our best ideas today. But in any case, there's a few points I want to make that will make this slide more clear later, I think. So this is something I came across this came up only, I read it yesterday, but it happened just 2 days ago, that apparently the Italians are the first in the world to make sustainability and climate change mandatory subjects. And they're going to incorporate the UN's 2030 Agenda for Sustainable Development. And even math and physics courses will be taught from the perspective of sustainability. Now, I don't know how they're going to do it, but this is exactly the kind of thing I have been thinking about for the past 10 years, that how do I, as a physicist and as someone teaching physics, how do I incorporate the essentials of climate change? And it's tough. This is a tough job. So here's how I've been thinking about it, is that yes, we are ethically obliged to teach this stuff because it is an issue of intergenerational and other kinds of justice, but it's difficult. We are not prepared for it. We have siloed education systems where the disciplines don't talk to each other, right? And in this education system, it's very difficult to have this sort of approach. Plus, this stuff is depressing as hell. So, and yet we have to tell the truth. That's part of our obligation. So, and yet, is it ethical to put such a huge burden? So you're giving the younger generation a ruined planet, and then you're giving them a hell of a depression about it. So we have to find our way through all of these. So this is such a fraught topic that we have to employ the best practices we have to teach this stuff. And so what I've been doing before I got into teaching climate, I was looking at different kinds of pedagogies and developing them for the physics classroom, and I was already interested in interdisciplinarity. So these are some of the things that have inspired me, and I'm not going to go into details about a lot of them, but it's really important to have a cultural atmosphere in the classroom that's based on trust. And I'm not an expert on some of these things, but I've read enough about them that I have experimented with them and played with them and used them in the classroom to good effect. The things that I have worked most with are the growth mindset. How many people know about the mindset stuff? Okay, great. This is so worth learning about. It's transforming education everywhere. The research that Carol Dweck, who's an educational psychologist from Stanford University, what she's done is really remarkable. And then Ken Bain, who is famous for a book called What the Best College Teachers Do, compiled a bunch of best practices for over 15 years and created something, a model which he calls the natural critical learning environment, which has 15 key elements, and I've only noted a few of them. But, and if we have time, I'll get into details as to how I implement all this. So I guess what I'm trying to emphasize with this slide is that whatever your best practices are for creating a classroom culture where students feel psychologically safe so that they can be emotionally and intellectually challenged, that's absolutely essential if we want to teach climate change well. So here's what I've kind of outlined here. Is that, and this is kind of the path I took, with a few stumbles along the way, that the first thing I did was to figure out where climate change intersects with my course topic. And it was very clear to me where it did from the beginning, at least the basics of it. And then I realized that wasn't enough, so I needed to extend the ideas. And I'll show you a table in a moment that I lay out as to how I integrate these topics. And then I tried to look for what was missing. Based on my conceptualization of an effective pedagogy, what was missing? And clearly, the scientific technological dimension is there, but the others aren't. So I had to find a way to integrate those. So here is an example. I'm sorry this slide is not too terribly clear, but I'm happy to share information with people over email if you're interested. So here it is that I laid down a list of physics topics that I teach in a general physics course, and I looked at the topics that I can extend to climate change. And I don't teach all of the climate change topics listed here in all my physics classes. In fact, there are some physics classes, like for instance, I teach a course called Physics, Nature, and Society, which is an interdisciplinary physics course for non-science majors. So because we have an interdisciplinary mix here, I'm mostly going to speak about that class. And in fact, I think I've had the greatest successes with that class. So I take some key topics, and that's one of the things I had to struggle with, by the way, is that what are the key essentials of climate science that everyone should know, so that they have an understanding that is inoculated against misconceptions and fake news and all of that. And so that's a question that I'm going to come to in a moment. But to continue with what I do, in order to integrate the other aspects of climate change that I think are necessary for an effective pedagogy, I actually have a climate week. So where we take a big picture view of what's happening. I connect climate concepts via three what I call meta concepts, kind of overarching concepts, which give you a kind of conceptual structure on which I can kind of hang the ideas. And then I introduce complex systems. I connect that to climate change. We look at evidence and impacts. We look at climate justice. We look at what needs to be done, what are the barriers. And we start an interdisciplinary project. And sometimes we start this earlier in the semester. Although I say it's optional here, I found that even a simple interdisciplinary project it's better to do it than not. And I'll tell you about some of the very basic ones I've done, as well as more ambitious ones that I've done. So in any case, so here's what I want students to do. I want them, these are our takeaways, that we want them to know, and this is a very popular, this has been circulating for a while, that climate change is real, it's very serious, and the third bullet point is usually it's us. But I like to say it's some of us, because it's a justice issue. So that's how I put it. I put the parentheses there. It's happening now. And I used to say, way back when I started in 2007 as an innocent physicist, my last bullet point used to be, we can change it. We can prevent climate change. And I'm so sorry to say that every year since then, and I'm not even sure that we can prevent catastrophic climate change. But in any case, this is what I want them to walk away with. And so what I do is I start with the first thing that if you go back here, I start the semester with a contextualizing discussion. And so this is what I do. Firstly, climate change is in the syllabus. And taking inspiration from Ken Bain's best practices, what he calls the promising syllabus, I pose a question, and it's a question about climate change, and it's posed in a way that my hope is that it's something interesting to the student, a question that is relevant to their lives, like how may climate change affect you? And what, if anything, can you do about it? And I have a picture usually, and I have a paragraph describing some things about it. And I send that invitation to students before class. And then we discuss it on the first day. And I try to get a sense of the baseline. What do they know about climate change? What are they thinking about it, feeling about it, and so on and so forth. So, and then, probably about a week or so later, we go to the planetarium. My university is very lucky that we have our own planetarium. And we look at 3 images of Earth. We have a beautiful planetarium program called the Layered Earth, where you can actually rotate the sphere and so on. This is all satellite data. So the first one is the big one, the planet Earth. And I asked them to identify key large, large features of the planet as though they were aliens visiting from elsewhere. And so they come to the obvious things. They see clouds, they see the oceans, they see the land, they see greenery, and so on. And we can rotate this so that they can get a sense of it. So this is their way, or my way rather, of helping them recognize what Earth scientists consider the key subsystems of our planet, okay? And anyone can do that. You don't have to be an Earth scientist to do this. Then the next thing we do is we look at the globe at night. And when we look at the globe at night, we see lights, bright, dazzling lights in many, many places. Western Europe, the US is ablaze. Lots of bright lights in India, lots of bright lights in certain regions in China, lots of darkness in other places. And I ask students to hypothesize what could be going on here. Why is it that some places are lit bright and others aren't? And by this time, we've already talked about what a hypothesis is and how, in order to study science or any scholarly endeavor, we must be bold enough to hypothesize without fear of being wrong. So the students are usually comfortable by this time, most of them. So the typical hypothesis comes up that it's got to be population. Wherever there's more population density, you have brighter lights. And then I show them a map of population data overlaid on the globe. And they see that while their hypothesis seems to be borne out for some places around the globe, it's not borne out in others. There are regions of high population density in Africa, large regions that are completely dark at night. So that's when we start talking about inequality. And since students by this time have some sense that somehow turning on the lights contributes to climate change, these 3 pictures immediately bring up all of the different dimensions of the climatic conversation, including the conversation on justice. So this kind of primes them to think about justice integrated with all of the others. So then when I get to climate science itself, what are the essentials of climate science that if you're not an earth scientist, not teaching a climate science course, what is it that you need to convey to students, and how might you do it? So I had to struggle with this. What are the key processes and concepts? And I'm still learning. So, and I'm learning from climate scientists. It's wonderful. But I'll tell you where I am right now. And then, of course, the question of how to connect and how to integrate. And one key problem you have if you're not teaching a climate science course is how do you avoid the piecemeal effect? If you have little chunks scattered throughout the semester, well, students are going to forget. Students are going to not connect them together. And what we want is a holistic understanding. So how are we going to do that? So here are the climate science concepts that I introduce, starting with these key questions. Is climate change really happening? How do we know that it's not just a natural process? What's the evidence that there's a human fingerprint? What factors affect the Earth's climate? And what can we do? And how can we evaluate all these solutions that keep coming up? So this is what I do. I use this picture which I came up with over the years, actually, in order to put everything about climate that I'm going to teach on one slide, or almost everything. It's not quite everything. And I use this picture as an anchor. So what I do is, the students have this as a handout, but I also project it. Every time we do anything to do with climate, I put this picture up there. If students have to present something to the class, they have to do it in the context of this picture. This picture tells them that although we are only able to do, let's say, a little bit of interaction between this and this and this system, or that and that and that system, there is actually a big picture out there. and they can fit in whatever they're learning through this conceptual structure. If I have time, I'll get more into details of this, but I'm mindful of the time limitation here. So let's see if we can get to that. But you can see here that I do not, for instance, use the term Anthropocene or Anthroposphere without disambiguating it. So typically, one of the things we know is that modern civilization's impact on climate is now on geological scales, right? And so that circle at the bottom is often labeled the Anthroposphere. But I put it in quotes because not everyone is responsible for climate change. And so what I do is I put marginalized human groups kind of within the biosphere here. And when I say marginalized, I mean people with less power who have not contributed substantially to climate change. And that includes the global poor, the people of color in many places. It includes indigenous people, and it includes the young who have not lived long enough to contribute substantially to the problem. So right there, front and center, in this system, climate justice is integrated with what we're doing here. The other thing that I want to point out is that this big circle represents the Earth, but it also represents planetary boundaries, and I'm going to talk briefly about that as well. And the idea is that it represents the limit where, and I've taken a lot of inspiration from Stockholm University's Stockholm Resilience Institute. Their website and the courses they offer free online are really, really great. I also want to put in a comment about David Archer's courses, because when I really started getting into learning climate science, I learned from his courses. I learned from his online course. I did all the homework and all the exams. It's worth it. They're awesome. All the models he was showing, they'll deepen your understanding of the science. So let me put in a plug for that. But anyway, so all of the key concepts that I think are important so far, anyway, at this stage of development of my concept, are in here on this slide. So if we have time, I'll go into more details about these, but I'm going to kind of quickly brush through them and get to, so that I can finish my talk and so that we can have a discussion, which is what I'm really looking forward to. But from all the things that I've studied so far, it seems that key to understanding the climate is the issue of balance or steady state, if you want to be more technical, and not steady state. So either some things are in dynamic balance, or they are kind of going towards some other, they're not, okay? And then the idea of planetary boundaries or limits, because when you have balance, when you have a situation of steady state, then that implies that certain parameters, if they are changed in some way, can perhaps push you to a non-steady state where you are going towards another state that may or may not be conducive to the existence of human civilization. All right. So boundaries are suggested by the idea of balance, but also complexity, and I'll talk more about that in a moment. So here are the concepts of balance and imbalance here that come in. And so if you understand what this concept means, well, actually you really understand it through two key processes. One is the greenhouse effect, of course, which I had started teaching way back when I first started this. And then when I realized that students were wondering whether breathing out was contributing to climate change, that I really had to learn and teach the carbon cycle. And so the carbon cycle is really key to that. And the important thing to remember is that a steady state or balance or a non-steady state can be due to natural causes. Because if you look at the Earth's deep history, Earth's climate has changed naturally and dramatically on its own without any human assistance. And so what I'm calling balance and imbalance is in a way tuned to the human condition. What would be good for us? Certain steady states would be good for us, certain steady states would not. Okay, so take that as a caveat there. It is a misconception that the natural systems are always balanced, okay? But that's not always true. So it's important for students to realize that. But we know now that modern industrial civilization is unambiguously the cause of the current imbalance in atmospheric CO2 levels. In other words, CO2 levels are rising, they're not, so Dr. Archer's kitchen sink example, the water level is rising, not staying steady, leading to global heating and climate change. So I talk about, I'm going to just run through these slides because I think that you don't need to see these in that much detail. So the greenhouse effect, greenhouse gases, and I show this graph. So I have a few iconic graphs that are really, really rich with information. And this shows us, for instance, that from about 800,000 years ago to the present day, this is an older graph, but I like it because of the scale. This was made in 2008 when carbon dioxide levels were less than 400 parts per million. And you can see the ups and downs from prehistory, where the ups and downs represent the glacial and interglacial cycles, where only a change from 200 to 300 parts per million of carbon dioxide lead to the difference between the northern hemisphere being mostly covered by glaciers and the kind of climate we have today. And then we have like basically blown it for the next glacial era, as far as I can tell, because that spike starts out from about the 1880s when people started burning fossil fuels on a mass scale for the first time, start of the Industrial Revolution. And then there are a couple of scenarios here. So, and then there's more detailed short scale graphs. I show the global temperature rise, and I talk about how the 1 degree Celsius rise compared to pre-industrial times is actually significant. So I spent some time talking about why this is important, even though day to night temperatures vary much more than this. And I talk about the carbon cycle, which I'm not going to really go into, except to emphasize one of the things that Dr. Archer said, which was that essentially what we are doing is the carbon cycle is roughly 3 scales. And the short scales are basically shown over here. And then what we are doing is we are adding fossil fuels to the atmosphere. We're digging out carbon in the form of coal and oil, which is sequestered away from the short-term carbon cycle, and we're burning it, and we're putting new sources of carbon in the atmosphere. So it's exactly like the bathtub analogy, that you're opening the faucet more, and you're blocking the drain because you're undermining carbon sinks, like cutting down tropical rainforests. So the water level is rising, CO2 is rising, and so on. So one of the things I wanted to mention is that even within these scientific meta-concepts, as I call them, the issue of justice is always entangled. So for instance, we can ask who's responsible for upsetting the cycle. And if we look at that, by country, currently China, US, India, Brazil, Europe. Historically, we know US, Western Europe. But if you look per capita, US, Australia, Canada are among the top 3. And then income level is really interesting because the richest 10% of people produce 50% of the planet's individual consumption-based fossil fuel emissions. This is from an Oxfam report. And the term climate apartheid is one that is worth that everyone should know about, because that refers to this. I read about at an article from United Nations University, that climate apartheid refers to the fact that the rich will most likely, at least in the short term, get away with or at least protect themselves from the effects of climate change, which they caused by this statistic, while everyone else goes to hell. And in fact, we know that the super rich are already constructing luxury climate bunkers to protect them, and they've even got they're even like getting security ready because they expect the violence of the masses as the world goes to hell. So this is a pretty dire scenario, and of course by organization there are only 100 companies responsible for almost 3/4 of the greenhouse gas emissions. So here too we can bring in the justice issue. Now here's the thing, I mentioned that balance in a sense implies a boundary beyond which you go into imbalance or non-steady state. So the work from Stockholm Resilience Center at Stockholm University, I encourage you to look it up. They've done a fabulous job. Their research reveals 9 planetary boundaries within which they say is the safe operating zone for human civilization. That if our economics, if our way of life violates enough of these boundaries, then we cannot survive as a civilization on this planet. And among the boundaries, of course, are climate change, biosphere integrity, ocean acidification, and a few other things. So taking this idea of boundaries and applying it specifically to carbon dioxide emissions, we know that in 2009, world governments in the Copenhagen Accord basically said that we need to stay below 2 degrees Celsius. Later on, the Paris agreements, and it was actually the small island nations and the African nations who said, are you nuts? 2 degrees Celsius is too much. And they got everyone to push down to an aspirational 1.5 degrees C. So the interesting thing is that in 2011, a paper came out in Nature, which basically where somebody did a probabilistic calculation on how much carbon dioxide one was allowed to emit in order to get to 2 degrees C. And they came up with a number. And it turns out that the governments and corporations of the world already have in their reserves about 5 times. So if you burnt their reserves, you'd get 5 times the so-called safe limit of carbon dioxide emissions, which is actually not safe. In fact, the IPCC special report from last year talks about 1.5 degrees C being, so they're basically saying 2C is not safe, and 1.5 gives us a difficult but far less catastrophic world, avoiding major irreversible damage to the biosphere. And what they're saying is emissions need to be cut nearly 50% by 2030 and 0 by 2050. And this would mean unprecedented, far-reaching changes in all aspects of society. So as the writer Margaret Atwood said, it's not just climate change, it's everything change. And so that's what we're talking about here. So, and yet, look at what's happening. Talk about breaking boundaries, just look at that. Global emissions went up 2.7%. And there is a global justice argument that countries like India have made, Brazil has made at the UN, that developing countries, especially those who were suppressed by colonialism, need to emit CO2 because they need to be as prosperous as the other countries. And so it's the rich countries that should cut their emissions. And that argument has some logic to it. The rich countries should, in fact, take the lead because of their historical culpability. However, this assumes a few things. It assumes that there's only one path to only one kind of development. And it also assumes that all that burning of CO2 that's going on in the developing countries is happening to uplift people out of poverty. Well, if you go back to where my parents stay and look at the number of malls that have come up on one street, all with air conditioning and expensive products, then you'll see that they're not actually thinking about the villagers in the back country out there. So there's some ways to mess with that argument. So just to sound the dire note, as though I haven't already, we are headed for a 4 to 6 degrees C temperature rise by 2100 if it's business as usual. Remember, we're already at a 1 degree, and we are being warned that 1.5 is as far as we can go, but this is where we are headed. So how do we understand all this stuff? How do we understand, how did this happen? Like, how is it that there weren't more warning bells? And actually there were. Scientists have been yelling about this for decades, but why is it that it somehow didn't where's the ripple effect? What happened? So to understand the historic moment, but also to understand how this can come about so quickly, like how has this change happened so quickly? We really need to understand one key essential feature of the climate is its complexity. So I always do a little unit on complex systems, which really is not something that is limited to a scientist because complexity is everywhere, as we'll see. So complex systems are basically those that consist of many interacting parts in which the interactions are strong and non-trivial and can even change the nature of the parts. And they're just as important as the parts themselves. And so this is the Aristotelian dictum that the whole is greater than the sum of its parts. And I will talk about a historical hypothesis that I have as to why we don't think like this normally. But let's talk about what complex systems are first. So complex systems science is so new that people are still arguing about what a complex system exactly is. We kind of know it when we see it. We agree on its general features, but there's no clear definition quite as yet. However, look at these examples. These are all real-world systems. This is the everyday world we live in, right? Human social networks, the global financial system, ecosystems. Ecosystem biologists were among the first complex systems scientists. So hats off to them. So the global climate system is certainly complex. You can consider the atmosphere, all of those subsystems as parts, but they interact in highly nonlinear ways. So we'll talk about that. So here are some things we know about complex systems. They tend to share certain common properties. They often have feedback loops. I'm going to talk about one. Dr. Archer mentioned a couple. And where a feedback loop can be what is called positive, not in the sense of good, but in the sense of additive. But perhaps we should use the term destabilizing, because that's what they can be. And also stabilizing feedback loops, which can interact with each other. So feedback loops exist also in simple systems. But in complex systems, there are many of them, and they can interact with each other, typically. And their behavior is not linear. They can undergo sudden changes, surprises, tipping points. Certain small effects can accelerate very quickly. So here's one, the most famous one of the climate system. So one of the things we know is that shiny surfaces are reflective, right? So the sun shines on a piece of white paper, and the heat and light are reflected without absorption, which is why people in desert countries tend to wear white, which is why if you wear black on a hot day, you feel really hot, right? So in the North Pole, we don't have land, we have ocean, we have the Arctic Ocean, and that's covered by frozen seawater, which is the sea ice of the Arctic. That's different from Antarctica, where if ice melts, there's more ice underneath it, 2 miles of ice, right? But on the North Pole, if the ice melts, now it may be from centimeters to a few meters thick. So if it melts, then underneath it, it reveals dark water. Water being dark can actually absorb the sun's heat and light. And so through enhancing the greenhouse effect, it can retain some of the sun's energy in the Earth system. And in fact, that's exactly what happens. And this is one reason why the Arctic is warming at twice the global rate, because of this destabilizing feedback loop, as you can see. So you warm the Earth and the atmosphere by burning fossil fuels. That causes ice to melt. That causes more absorption of the sun's radiation, which enhances the greenhouse effect, which makes the Earth warmer, which makes more ice melt, and I could go on and on and on. So this is a vicious cycle, in other words, in everyday language. Yes? So this is only one destabilizing feedback loop, but there are many others in the climate system. And what these sort of positive, in the sense of destabilizing, not good, feedback loops can do is that they can accelerate and amplify climate change. And when you have many, many interacting destabilizing feedback loops, or even one that's strong enough, then you can actually take the system towards tipping its state to an entirely new state, all right? And that's essentially what is happening. And tipping points are, well, there's also something called a tipping element, but I won't go into that. Tipping points are points beyond which the climate system undergoes a drastic, systemic, large-scale change, which is usually irreversible at least on human timescales. So here's another example I'm going to give you. Oil drilling in the Arctic Ocean. In 2013, December, the Russians started the first drilling rig in the Arctic. There's been exploratory drilling in the American Arctic, like off the coast of Alaska for some time, but no actual drilling has started yet. And the idea here is that as the Arctic melts, the reserves of oil and natural gas on the Arctic seabed are getting easier to get to. And many of them are in relatively shallow regions of the Arctic, all right? So what the fossil fuel companies are saying is, wow, the Arctic is melting, so we can get to all that oil and gas, we can extract more oil and gas. And I hope you can see what this is. So the more you melt the Arctic, the easier it is to get to those oil and gas reserves on the seabed, the easier it is to extract them and then burn them, and then that causes more Arctic melt, and that is another destabilizing feedback loop, which interacts with the ice albedo feedback. So the Arctic drilling hasn't started in enormous earnest, but I know that from a geopolitical perspective, the Arctic is being looked upon with, shall I say, avarice from a lot of countries and corporations. To put it in context, we know that what fossil fuel companies and governments already have in reserve is enough to fry us 5 times over. And they're looking for new sources of fossil fuels. And that's only going to make things worse. So it's through the complex, through understanding feedback loops and interacting feedback loops that students understand that you cannot just wait for Boston to get as warm as North Carolina and then fix the climate. It's like we don't have that much control over it anyway, but the point is that when you have enough destabilizing feedback loops set into the system, they are set in the system, and the system has some inertia. It's going to go, it's like if you have bad brakes on your car, you might brake, but you're going to keep going for a while. And we're not even braking yet. So, and by the way, I had an interesting conversation with a student once where I taught the complex systems bit to my students, and they were supposed to do a project on climate change, and everyone was depressed, and this was before I became more interdisciplinary. And one student was like just crazily chipper. And she was generally a very cheerful person, but I wondered, and I said, why are you so cheerful about this stuff? And she said, well, professor, you know how you said that human social systems are complex systems? So I said, yeah. And I said, I'm not a sociologist, but I do know that to that extent that's the case. And she said, well, if climate systems can have tipping points, maybe we don't have to kind of wait for everyone to get on board. Maybe we just need a few small key changes that can change the system as a whole. In other words, some kind of sociological tipping point that tips us towards a more responsible, a more humane, a more just society. I'm paraphrasing a little bit of what she said, but essentially that's what she said. And that was one of those moments when you go, boy, do I learn stuff from my students all the time. So I wasn't expecting that. So anyway, so we always come back to this picture. We always come back to this and say, okay, so can you describe the carbon cycle, through this picture? Can you describe the greenhouse effect? Can you describe what's happening? Like, is that circle at the bottom getting fatter and kind of pushing us across the boundary? And if so, in what way? Or can you describe the justice issues? So you see how this picture becomes a kind of anchor that, so far at least, I have a sense that it avoids that piecemeal death trap of trying to teach climate change in a course that is not about climate change per se. So it works as an anchor. But then, to go back to the point I made in my slide of student reactions and misconceptions, we are dealing with young people who already have, at least for my students, a lot to bear, a lot of responsibilities. And I don't know about you, but I've seen an uptick just anecdotally on the amount of anxiety and depression anyway amongst students. I don't know if you've noticed that. We are teaching students that are very, very different from the ones that were around 20, 30 years ago, I think. That's just my anecdotal sense. But actually, it's not entirely anecdotal because we know from a Cigna study, I think it was earlier this year, that there's an epidemic of social isolation among Americans, particularly among the elderly, which is not that surprising, but also among young people. So stuff is going on in societally and sociologically that we need to pay attention to. So we have to give our students means to deal with the psychological weight of all this stuff. And in fact, climate scientist Steve Running came up with this. He said that this stuff is so depressing. In fact, think about it, that learning about the possible end of the human civilization as we know it, the biosphere as we know it, is such a devastating emotional trauma that our reaction to it surely must be analogous to the way we react to any grief or loss. And we already have a guide. There's something called the Kubler-Ross grief and loss scale, which I don't know if you've come across. I had to go way outside my comfort zone to develop all this stuff. But when we grieve, let's say a personal loss, someone close to us passes away, we go through stages where we kind of try to pretend it's not happening, or we get upset that they left us, or we try to see that, that maybe it was their time or something like that. And we generally shy away from grieving from the depressed state. And we get stuck in these stages, and it's only when we accept the truth of what's happened that we can be free of grief. So Steve Running, climate scientist, made this proposal that maybe there's something like that there are 5 stages of climate grief. And then others added a 6th stage, which is doing the work, where you are free enough that you can roll up your sleeves and say, all right, it's bad, but what the hell, I'm going to do this because I have to. There's no other choice. So what I do is I make this transparent to students after the first few times that we've really got into climate science and looked at the evidence and impacts and so on. I ask them how they're feeling about it. Now, that's not what we are used to doing in a science class, but we can't do what we're used to doing anymore, it's my opinion. So I ask them how they're feeling about it. They share their feelings. And recently, I've had a psychologist colleague has been coming into my class and doing a study on the affective response to learning about climate change. So we make it clear, and I tell students that what they're feeling, everything they're feeling is valid. It's what they're feeling. And that there's actually a way to get through all of these stages. But I also ask them to be critical. I say that this is a hypothesis. Are there other stages of feelings or whatever? Is there something that we can improve on this hypothesis? So they become kind of fellow investigators of their own individual emotional reaction as well as that of the community of the classroom as well. And we want to talk about, and I tell them also that it's totally okay to know that you're going to have to cycle through these stages many, many times. It happened with me. I share my story of how there was a time I couldn't bear to look at any more climate science stuff. I just could not stand to look at it. And then I had an experience which helped me get through it. And part of it is we tend to avoid grieving. And we have to grieve. We have to grieve for the world we've lost. We have to grieve for the species that are going to be extinct. 1 million species under danger of extinction, according to a new UN report on biodiversity loss. We have to grieve the future we won't have, that our children won't have. And if we don't do that, if we are not bold enough to do that, then we won't get through these stages. But you can't grieve something of this magnitude alone. You have to do it in community, which is why the community aspect of the classroom is so important when you go through this, when you do this kind of climate pedagogy. So I talked to them about this, and one of the things that I've done about 3 times is that I've had an environmental poet, one of my colleagues, come into the classroom, and this is where the humanities can make a huge difference to dealing with this stuff. We really, really need the humanities, not only to communicate the climate science and the dangers, because scientists can't do it alone, and scientists typically are terrible communicators, but we also need the humanities for us to work through this stuff. So this is really, really important. And students who were like science majors, who didn't think of themselves as poets, who kind of looked down on poetry as a means to think through their emotions, were utterly stunned at what they produced and how it helped them feel free to roll up their sleeves and say, okay, I'm ready to get to work. So one quick thing I want to talk about, and I am already out of my personal time frame here, but I'm going to try to talk about this quickly, is that we have to try to help students and ourselves understand how the heck did we get to this point? And how do we think through this place? So I start with defining a paradigm early in the semester, which is a framework or a set of assumptions for thinking about the world. Many of them consist of default, unconscious, unexamined assumptions. And most familiar are scientific paradigms. So for instance, the famous one, the transition from geocentrism to heliocentrism, was a huge paradigm shift. And this is something that Thomas Kuhn wrote about in his famous book, The Structure of Scientific Revolutions. And the term paradigm shift has been misused so much that it's a buzzword with almost no actual substance anymore, but it really does have a deep meaning, which if you read Kuhn's work, it really is really interesting. And so what I tried to do was to talk about what I call the Newtonian paradigm. Now, this is not my conceptualization necessarily, but I'm bringing different threads together, and different people have talked about it in a similar way. So basically, the Newtonian paradigm has to do with how science and history changed when Newton's laws came into the world, right? Newton's laws of motion, Newton's law of gravitation, and of course that has a prehistory to it. It is not at all unconnected with the colonizing imperative. So there's a lot of history here that's entangled. What I'm doing is I'm drawing an oversimplification of history, but in the sense, with the hope that it's a useful oversimplification, as Steve Chapin, who is a sociologist and historian of science at Harvard, puts it in his book, The Scientific Revolution, that sometimes oversimplifications can be useful if they're honest oversimplifications. So I'm trying to do that. So what Newton came up with was a controllable mechanistic universe. So if I toss this bottle into the air, then with just a little bit of information about the initial conditions, I can predict exactly where it will be for every point in its journey for every time. And so there is a kind of control, a precision, a predictability about this view of Newton. And the trap we fall into is assuming that the entire universe works that way, as we'll see. So one analog for thinking about the Newtonian paradigm is the clock. In fact, it's also called the Clockwork Universe. This was a philosophical idea that came up thanks to Descartes and other people later on, that the universe was controlled by natural law. So you could think about it as a clockwork machine. And so all God had to do was to wind up the clockwork and then let it tick. And this is a very powerful and important idea, not least because it gives us the notion of democracy that Thomas Jefferson refers to the inalienable rights of man, referring particularly to the natural laws and so on. So it has a long, long shadow, all of this. So in any case, this clockwork universe, however, where everything is predictable, controllable, where you can, if you understand the parts of a clock, take it apart, look at the springs and gears, you've understood the clock. It's a reductionist system. You can reduce any system to its parts. Understand the parts, you understand the whole. All right, very powerful idea. It's carried science very far. But there were protests. So here's the poet William Blake with his painting of Newton looking at one part of the universe while the rest lies undiscovered around him. And in fact, he said, "And God us keep from single vision and Newton's sleep." So this is the Newtonian paradigm, the clockwork universe. And it seems to me that this is something we're deeply affected by even today. The atomism of it, consisting of separate and distinct, well-defined units, the determinism of it, we can control this, we can control that. The fact that we are separate from what or that we think we are separate from what we observe. But we know from my own field of physics that the universe is not, says the universe, excuse me, I am not Newtonian. And this is, the 2D plot over there is something that is in actually a few textbooks. You can see that Newtonian physics occupies a small little box over there and is superseded by more accurate theories. What I've done is to extend, make a z-axis, extending it out, and to declare that Newtonian physics can only really wrap its head around or is most useful for simple systems, even at our scale. And when you get to complex systems, then although they're deterministic, you lose the kind of Newtonian predictability that we have. So I'm not going to go into details because I'm going to be out of time really soon, but I've had this discussion where we talk about how if you are immersed in a paradigm and you don't know that you're immersed in a paradigm, you suffer from what you might call paradigm blindness. That you just take the default, you don't question the unquestioned assumptions. And so I'm not going to talk in too much detail about that, except that in part, the reason why we do not see a way out oftentimes of the mess we are in is because we do not know how to think outside the Newtonian box. That's my hypothesis. And that's why the problem of climate change is also a problem of the imagination. So always climate justice wraps around the meta concepts and is also something that we study of its own accord. I typically take a case study of some kind, and if I have time, I'll talk about that. But I've already mentioned this. And what is interesting is that often we look at these groups as victims, and in a sense, they are certainly the unintended or the recipients of the mess that has been created. But also what we overlook sometimes is that they may have the real solutions. And in part, it's because they may have alternative epistemologies. If our epistemology arises from this box, well, if you think about it, complex systems, if you look at indigenous cultures, and there are many, many different indigenous cultures around the world, they're not monoliths, but one of the key common features I've found in my initial investigations is that they seem to take complexity as a given, as a starting point. Whereas we come to it from reductionism to complexity, they start from complexity. And they have some really, really important things to offer, epistemologically as well as practically. So I'm just going to show a couple of slides more than a couple, but very quickly. For instance, look at indigenous people. They are only 5% of the world's population, but they manage about 80% of the planet's biodiversity, including an enormous amount of carbon. Okay, and wherever you have indigenous people with legal rights to their land, that's where the forests are the healthiest, they have the thickest tree cover, and so on. And yet, it's the indigenous people who are our first climate refugees. So this picture is from Louisiana, where there's the first climate refugees in the US are being displaced. The other picture is from Alaska, where a barrier island village of Shishmaref is being relocated because it's falling into the sea. So one of the things I always teach, and in fact I have students do this, they research climate movements. This is one way to really inspire students, because once they get into that blue funk, and we work through the psychology, they get through that a little bit, but then they want to know what to do. And I'm going to quote Bill McKibben, who used to say that, well, here's what you can do to fix the climate, and he used to point to various actions you could take at home and so on. And now he basically says, you want to do something about climate, join a movement or start a movement. Because it's in collective action that perhaps we can change the infrastructure and have the systemic kind of changes that we want. So I have students investigate and report to the class on climate movements, and that gets them pretty excited. So I'm just going to end with a couple of slides here. This is from Extinction Rebellion rallies recently, and this is from way back when the Standing Rock Sioux were defending their lands. The pipeline was built. You may have heard that it spilled some 300,000 gallons of oil just a few weeks ago. Yeah. And I want to show a picture of an indigenous elder in the Amazon, which is on fire, along with the Congo, along with forests in Spain, along with California, and how these people are the ones who are being murdered. Indigenous environmental activists are murdered at like unbelievable rates. And yet they keep persisting, and they're protecting us, all of us. So we talk about developing and trying to develop a justice framework for evaluating solutions. I won't talk about that right now. But just lastly, two things I want to end with. One is that the projects are really, really important. And the more ripple effect they have, the better. So if you have something where, let's say you have an art class and you do drawings and you display that to your community, think about it. Is it a sufficient ripple effect? If it works, if people are excited by it, do something to expand it. Maybe make it viral. Talk to the next school district, have them do it. You see what I'm saying? So we can't think in our little institutional boxes or classroom boxes anymore. So the ripple effects are really, really important. And so that's why on the handout that I have, there is a little tool that I'm experimenting with. I don't yet know whether this is going to work or not, but I would love your feedback if you feel like trying it at the back of this sheet, where we stop thinking about individual solutions and try to go to larger scale solutions. And I've had, I'm not going to talk too much about results, except that I'm still working. This is still a work in progress, but there are many, many promising signs. And if you have time with questions, I can talk about that. I'm still in the process of developing this framework. And what I'm going to end with is basically indigenous people, a tribe in India, in eastern India, which is being threatened by a mining company. And they actually won. They went all the way to the Supreme Court and they won. And one of the things that they, people were surprised that they did not want their forests razed down and displaced to somewhere else, and that they had turned down promises of, cars and roads and television and all of that. And essentially they said, we don't want to live like you. You all look so miserable. Your cities are horrible. We don't like that. And in fact, that's what this particular leader, Lado Sikaka, said, that why should I give up my hills? I get everything I want from, and to them the hills are sacred. And everything is clean, everything is free. They're not poor by their own standards. They don't have very much, but they have everything they need. They're independent of the modern industrial system for the most part. And so one of the things they're doing is they're saying, well, we don't want to live like you guys, but we also don't want to be isolated from the world. So they've been having community discussions when they're not being harassed by state officials and corporate officials and had false charges leveled against them and so on. They are having community discussions about what is well-being. What does well-being mean for us? I think that's a deep, deep question that's at the heart of the climate crisis, because we don't think about what well-being really means. And what is real happiness? And in fact, one of the things he says is that if they are displaced to the cities, their identities will be lost. And he talks about loss from his perspective, whereas if we are not aware of all the intricacies and so on, we might think, oh, these are the people, they're so poor, we should uplift them and put them in cities and give them lots of cars and television and so on, right? But he's saying we are going to lose something. So what I want to ask, because the climate conundrum is often put in the language of, hey, we are going to lose stuff. If we have to do something about climate, we have to lose, we can't use this, we can't do that, we can't do that. But the question I want to ask is, what have we already lost? What have we already lost by choosing the path that we took? And in other words, what is it that we have to gain if we change our path? And so what I feel is that the project for healing the climate is also the project for real human happiness on this biosphere. And I quote from the same warning that I showed you earlier, that the kind of transformative change we need is also a change towards greater well-being for all of us. And ultimately, the question is about what is well-being, because after all, there is no planet B. Thank you.
I just wanted to make one quick comment and raise this one question. When David Archer spoke, one of his former colleagues here was Raymond Pierre Humbert, and in his book, he mentions about the radiative forcing and the Stefan Boltzmann law, but he mentions that the Stefan Boltzmann law, you have the Planck's constant, you have the speed of light and Boltzmann's constant. So it brings together all these different paradigms, and that was sort of a model of what we had to do according to Pierre Humbert. But my question is, I think, isn't there one way we can really look seriously at this climate change issue from this perspective? We start with linearities, but we have to understand how the non-linearities arise through climate degradation, and maybe how they inject these climate tipping points into the system. And I might challenge a little bit your slides where you talk about Newtonianism and quantum mechanics. I don't think that's really the issue. I think it's determinism versus irreversibility, going to the Boltzmann and Prigogine paradigm, where we have irreversibility, which engenders this. And to me, that's a bigger issue. And I think if you look at these transitions between determinism and irreversibility, whether you have quantum mechanics or classical mechanics, it's going to be a much more better way of looking at this issue. What do you think of that alternative?
I think I might have to ask you to repeat some of that because I couldn't hear that very well. But could you just repeat your question about what you were saying about the, so I got what you said about Stefan Boltzmann law and nonlinearity.
No, the idea is not quantum mechanics versus classical mechanics, but determinism versus irreversibility. Like irreversibility, we teach the students about chemical change, and the laws there governing the equations are irreversible in time. How do we go from the time reversal invariance to the irreversibility, which is indicative? And I think that's a key issue that might possibly bring in these climate tipping points into play, rather than sticking with the reversibility paradigms of either classical physics or quantum physics.
That's right. Thank you for repeating that. That's actually a great observation. And in fact, we know that, and I know this as a particle physicist by training, that the microscopic laws of the subatomic realm are actually, for the most part, time reversible. And yet we have in the, in the everyday bulk macroscopic world, we have irreversibility. We have the second law of thermodynamics. We have the arrow of time. So I think when I refer to irreversibility and tipping points, where that comes from is the fact that the carbon cycle has that very long, the cycle that Dr. Archer was talking about, the stabilizing feedback loop of the climate, the weathering silicate cycle. It has a time scale of hundreds of thousands of years. And so that's what I meant, that on human time scales, that's irreversible. So a large fraction of the CO2 we put in the atmosphere is going to stay around for, a significant fraction is going to stay around for 100,000 years or more. But what you've raised is actually intrigues me as someone trained in theoretical physics. And in fact, that is an enigma. Like, how do we go from the reversible basic equations of the microscopic realm to irreversibility? And that's a huge and fascinating research question, theoretical research question. How do we, is there a way to go from those equations to the second law of thermodynamics?
There absolutely is.
And that's statistical.
Separation of time scales. You have all these time scales merged when you have reversible processes, but when you inject the time scale separation, you're able to get a irreversible equation which complies with the second law. The other things are the fact that you have this reversibility in time. It just seems to me that the climate change is somehow connected with this grand theme going from reversible dynamics to irreversible dynamics.
Well, of course we have, I mean, you're right, statistical mechanics gives us the way to connect those things, but I don't think we understand very conceptually how that happens very well. And I think you may be right that if you're saying that the climate issue is a general increase in entropy, well, of course it is. But how else it might connect, I think the jury is still out on that. But that's a very interesting question. Thank you for raising that.
Hello. Just a question. Is there anything you would explicitly advise against showing or exposing to your students at a middle or high school level?
I'm sure that people in the middle and high school level are actually best qualified to talk about that because you know your students. But I would guess that that's really tough. In fact, one of the places I lean on for climate information is, particularly in the psychosocial realm, is the Yale Climate Communication Project. And if you sign on with them, they'll send you an email with research on the climate, about climate change in the US and the world. And I know on their site, they have an article about how to speak to the young about climate change. Now that is more aligned along the lines of, the talk you have to have with them about sex and drugs and alcohol. Well, you also have to have a talk with them about climate change. And how we talk to them about it is obviously very crucial. It has to be in the context of your relationship with them. And it has to be, you have to give them the tools, and this is true for college students as well, to actually take their knowledge and learning and do something with it, and to know that there are other people around the world doing something with it. So that's what I would encourage.
Thank you. First of all, sorry, I'm really sick. Your presentation was phenomenal, and I've taught climate change before from an interdisciplinary model. And if it's at all possible for you to share your slides with us, because you had so many fantastic images that beat some of the stuff I managed to find, like that would be really lovely and helpful. And then my question is, one of the things that I didn't see come up in your presentation, but I found it was something that I'd focused on, and I'd like your feedback, and if it any additional resources maybe, or contextualizing what I ended up sharing with my students. The impact of food and diet on climate change, is it something that your students are interested in? Is it something that you explore in your classroom? And is it like a solution that you look to? Because like what we eat is drastically, like we're deforesting. We have deforestation because we're trying to raise cattle. And as countries become more wealthy, they're increasing their meat consumption, particularly of things like beef. And then you have like this double problem of cows that produce methane, which we just learned about. So any feedback on that as like a part of this complex system?
Yeah, well, I'm happy to share, so I'll talk to Matthew about that. Yeah, I think that's really, really important. And in fact, that comes up when we talk about solutions. So I haven't had time to put some of our discussions. And what I try to encourage the students to do is to take whatever aspect of the solutions discussion they have, for instance, and do a project on it that they can present to everyone. There are a lot of unknowns about a lot of climatic effects, very difficult to get our heads around some of the details because there's such lack of information too. Like for instance, how much carbon soils store. Like they've been like wildly oscillating figures on that for a while. But in any case, the point is we know that food choices are a huge part of the whole thing. So in fact, what might be, I haven't done this, but you're giving me an idea too, is that with that picture of the Earth with its subsystems, that one could discuss it in that context too. And in fact, that's what I'm trying to do with my solutions framework, is that you look at a solution or a proposed solution and see, is it exacerbating or is it kind of calming down the carbon cycle? Is it, what is the long-term impact of this so-called solution? And so that would fit right in because that's certainly a very, very important thing. The thing that I don't want students to do is to think that all they have to do is change their own food choices because it has to be a mass collective thing. So we do discuss a little bit, like I have often students in my class who are vegetarian and vegan and we talk about whaling in Alaska, and then we talk about how indigenous people have a relationship with animals that's different from our relationship with factory farms, and things like that. So it in fact goes for a very rich and personal discussion. And I should just mention quickly, the other way to make climate change real and personal is to talk about health, its impacts on health. And one of my classes did a project on that, in fact, for our town, for our city. Yeah, go ahead.
I've been teaching environmental biology for a long while, and now the past 3 semesters, I'm getting more and more students who are climate deniers.
Really?
And it's when you have a student that is a climate denier that, you could have a real problem with trying to convince the rest of the class. So my question here is anybody, having the same problem? Or is it just like, it's been just 3 semesters. Before that, all the students were okay, any projects were fine. So I'm just asking a question about how do we address this climate deniers that come to biology, environmental class?
I've had that early on, that problem, and it's a lot to do with the relationships that you have with your students. That's the only way I've found. Where if, and I used to have to tell my students lately, well, I'm in Massachusetts, close to Boston, but you all know about the Heartland Institute's publication that was sent out, right? The disinformation campaign and all of that. And I know Dawn's going to talk about ways that we can counter those things as well. But just very briefly, it really is in the relationship. When I have a student who's a denier, I tell them, I totally respect your right to believe whatever you want to believe. I'm going to treat you just the same as any other student. I show that. I care about them just as much as anyone else. But of course, they have to write the scientifically valid answers in tests and exams. All right. And what I've found is that they get softened. They get more open. They get more softened by the end of the semester to the idea that maybe there's something to this stuff. So I wish I had something more powerful to tell you, but I think it's really in the relationship. So
I would first like to echo a fellow teacher's sentiments that thank you very much for a very informative and inspiring talk. And at the same time, it had very practical suggestions. But harping on what he said, I was anyway planning, let me play the devil's advocate. Supposing there is a student or somebody. Now, we are very anthropomorphic. I mean, we try to see everything with human beings as the most important. Now, one thing you said that there are natural imbalances, just as there are human-made imbalances in these complex systems. Now, what do you mean by natural? When you say before human beings, there were other living species, and they were changing the earth, and before that, we can go back into it. Now, supposing, for example, we are what we are because the dinosaurs disappeared. I mean, they were reigning the world once. So what if some students say, this is the natural trajectory of planet A, our planet, and we are not supposed to be here as a species forever? I mean, I'm just throwing it at you. So if that is, then let nature take its course and let this go to its ultimate extinction. Like, the dinosaurs were extinct because apparently there was an asteroid and the climate changed and they couldn't adjust. So then mammals became predominant and we are the result. So if that can happen, I'm just throwing it out as an idea.
Well, that's a perfectly valid philosophical position to take, but I personally don't buy it. But, I encourage students to to defend their positions. Can you defend that? And if you can, fine, but there are people who, right, exactly. And always in a mutually respectful atmosphere, so, yeah.
Well, thank you so much. Everyone, again, a round of applause for Professor Singh.
Thank you.